Hello everyone. I hope that you had a good lunch and you enjoyed your lunch hour, and I welcome you back here to Quantum Karelia and the Karelia Auditorium. And we have a very special guest, the next Tuomo Kauranne. And I think that quantum computing and quantum technologies are an area where SMEs have lots of opportunities to build a quantum computer, bring in the mechanics and so forth, and algorithms. And now we are going to listen to Tuomo Kauranne, PhD. He's the president and he's the CEO and co-founder of Arbonaut Ltd. And we know Tuomo, of course, from previous sessions here in Quanti Karelia program. So welcome, Tuomo. The stage is yours.
Thank you very much, Christina, and thank you, Olli, first of all, for organizing this whole thing and getting me, for example, somehow interested about quantum computing. This is something that I'm really a newcomer and kind of prefer to stay an amateur, but not only an application specialist. I'm going to engage in some level of speculation. I hope I'm audible from here. Should I be sitting closer?
It should take quite a
while. Okay, fair enough. Yeah. So if somebody complains, please do start again. And thanks for the excellent and very vibrant presentations this morning. Mikael, especially, it's nice to hear you how the very impressive track record that IQM has made now. I'm looking forward to more stuff from Mikael and others. Who will have thoroughly enjoyed Joensuu night last night, but I trust that everything is fine and all right this morning. It's a long mathematical physical tradition to take life sometimes on the lighter side as well. So here we go. I'll first tell a little bit about, let's see, where do I get the pages going? Let's see here. Yes, okay. All right, that's all. And so, Arbonaut, just to give you a background, what kind of applications, why are we interested in quantum computing? Arbonaut is a 30-year-old company established here in Joensuu, and most of our staff, about 70 people, and 20 plus different nationalities. So we are somewhat behind IQM in terms of that, but the scale is the same. I think there's an important lesson for anybody involved in high technology, no matter where you are, fully international, internally and outwards. You have to be able to operate anywhere in the world. There is no other game except the global game in which you play. And Arbonaut technically is also part of that. So the map shows the countries where we have had active projects over the last 2 or 3 years that covers all the continents. Arbonaut's vision, Arbonaut's business and Arbonaut's mission in a way is forest information. So we gather, we analyze information about forest ecosystems and then help forest custodians and owners to make good decisions based on that scientific information. Our services cover the following 4 areas. There's first forest ecosystem inventories, often based on remote sensing and field data, ecological risk assessments such as forest fire mitigation, insect damages, and then forest information systems to manage forest resources, whether that be for conservation or for harvesting and economic gain. And forest operations management, that simply means that when you should do what in your forest properties. Our applications are based on always real observations, but they come in very many different disguises, all the way from field sample plots for ecological precision or validation of mathematical models, and then drones, forest machinery that now automatically collects more and more. Our main tool is airborne laser scanning, LiDAR, and that we collect both using autonomous vehicles like heavy-duty drones, fixed-wing aircraft, helicopters, and finally all manner of satellite information. And the general algorithm that we do is data fusion. So it means like mathematical, statistical, Bayesian estimation of what all this, plus our scientific knowledge of the nature of forest and geophysics tells us. And I'll show you some examples of the kind of computations that Arbonaut needs to conduct. So first of all, LiDAR. Modern LiDAR systems gather anything from 100,000 to 10 million pulses from the ground every second. And so we cover areas that range from, in the smallest case, about 10,000 hectares to millions of hectares at one go. That simply means an enormous amount of data, and also means that in practice, we had this discussion yesterday in the Rouge that we need to carry that with FedEx. So physical hard disk transport is much faster than any internet connection that we can transfer the data. This is what LiDAR looks like. And that also shows you why there's so much of information. So we get images of details of individual trees. Finland has maybe 100 billion trees. We cover them all, for example. And the kind of things that are calculated are related to the structure of the forest and the ecological and also timber quantity and quality type of variables. I'll pass them briefly here. So typically you want to divide your forest into stands, which are homogeneous areas where you can make a single decision for every stand or microstand. Trees, gaps between trees, that sort of things need to be calculated. Finland has been leading, so just like in quantum technology, I'm a mathematician. I ended up focusing on forestry first because I came here in North Karelia 40 years ago for a very good romantic reason, my wife and my family, but also because I realized I needed to plant science in a place where you have fertile ground for something. So my background was in weather forecasting, climate modeling. We'll come back to that in a moment. My high school was CSC, where Mikael worked, so 3 years in 1980s in that, in computational fluid dynamics, and finally supercomputer procurement became like the way to see that, okay, this is how high-tech business is to run. You need to be ambitious, you need to be global, you need to be the best in the world, which even currently is the case, I think, with LUMI, for example. So it's like needed. So in Finland, laser scanning in the forest has that property. It is the first and the only country that actually covers its entire ground regularly with airborne laser scanning for the very purpose of being able to do very accurate forest measurement. Arbonaut has a big share of that market. In fact, it's a duopoly. There's a Norwegian company in us, and even the Norwegian company is based here in Joensuu. So Joensuu justly is the world capital of forest science in many ways. So that also shows the scale. We do millions of hectares every year. This analysis, we need to process it fast. It doesn't have to be, in this case, very complicated. It's basically pattern recognition in high scale. So that could be amenable to quantum computing, since we are constantly constrained by the speed of our computers anyway. And these are the kind of things. So not only do we want to do good work, we also look for something good for the world and for the environment. And so things we search for example, are groups of dead trees that might host birds and rare species, sometimes even insects. We want biodiversity indicators. Right now, you may be aware we are still running this COP15 biodiversity meeting in Montreal, something where we are also engaged. Buffer zones for creeks and that sort of stuff. But there's another area which is also directly linked to forest, which is water bodies and water flow. And also this we have to do on a nationwide scale in Finland. So you see here the formal base of attraction of Finnish waters, but actually what we really have is what you see on the right, which is millions and millions of kilometers of small ditches that carry rainfall, that carry water, that go through peatlands, sometimes drained. Finland has this long-term policy of trying to drain peatland into growing forest, and therefore we have more ditches than any other country. We need to model them all, and this is also where mathematics comes into play. That we divide those into connected components in order to identify where water can go from one place to another. What is the catchment basin of the water body, or if you have pollution, then where might that pollution end up and where it definitely will not go. And you realize this is in principle a graph theoretic problem, but it doesn't behave that way. You have fluid dynamics. So what happens is where does the water flow, and that has to be computed by computational fluid dynamics. So the level of water on even a connected or disconnected graph network will change the topology of the network. And so we need to find out where they actually will go. Luckily, our CFD, the computational fluid dynamics, is relatively simple in the sense that it's often gravity-driven flow, and we only need to find the right slope and so on and so forth. Darcy flow in the worst case. But that shows the time scale. So do this on 30 million hectares every year, or sometimes every month, or every week. We might need quantum computing. So this was one of the reasons why I came here. Here's just some examples of how does it go. How can quantum computing help an SME? The first answer is yes. Unless you're an SME involved in quantum computing, like IQM, not a lot. And I think this is what we agree mostly on, and also based on what Martin Bakke was saying this morning. Okay, there's a lot of potential, and like Mikael, you said, this is the future, which is quite not yet here. So we are heading there. So what I thought that, okay, if this is the case, it's really important and nice to follow. We are very happy to use supercomputers, the classical ones, since this is like my growth. But I thought that, okay, maybe there's something we could learn for quantum computing also from the way that supercomputers behave, algorithms behave, and so on. So the rest of my talk, I will actually talk about parallels between these two fields. So I'm hoping to gain positive interference between quantum computing and an assembly, in this case, Jarmo. So some history, since I'm old enough to remember this. In 1980s, supercomputers were vector supercomputers, and Cray was the king of the field, as it still is in many ways, but it was a different company. Just based in the same small village in western Wisconsin, in Chippewa Falls, where the machines are still manufactured. That hasn't changed, although the orders and structures and so on have changed. They were based on arithmetic pipelines of fixed lengths that were able to compute very fast on a long range of, a long vector basically, doing the same calculation repeatedly over hundreds of thousands of elements, when there was no interdependence between successive program steps. So speed up typically was about 100-fold over a scalar computer. 10 years later, and we were into massively parallel supercomputers, so MPPs as they were called at the time. They had commodity processors, so Intel entered the game already at the time. They actually built their own parallel supercomputers, by the way, at the time. Intel IPSC was a prototype that they even sold several, so maybe kind of a parallel to what IQM is doing. But once again, no interdependence between the threads that run on different processors. So these were commodity processors, but if whatever each processor was computing should have, in principle, minimal dependence on what the others were doing in order to gain from parallels. Speed up was often 1,000-fold in this case. Here, two memorial pictures, Cray XMP on the left, and indeed this Intel IPSC from early 1990s. You can also see the similarity to the current computer architectures and why not even current machines. Then this interdependence between successive text. Here is an example. You have a loop on top, which every element depends on the previous one. So you have interdependence, and that will not vectorize nor parallelize. So you're in trouble. So why not to try the one beneath that we copy first the vector A into a separate vector, and then we have a second loop which doesn't have this interdependence. Silence. Anything wrong with this?
Yes.
Okay. So you realize it looks the same, but it doesn't indeed bring the same result. And this is where we come now to the interesting part. That whenever you design, it's very much the same as in quantum computing. You have to be careful that when you reformulate your algorithm for a quantum computer, you don't change the semantics. And that's an art and not a science. And there's any number of this kind of examples. This was just an easy case. So if we had like value 1 in the whole array in the beginning, in the first case we would get n, in the second case 2 on every element. Yet they kind of look the same. And this is why these automatic compilers and kind of tools we have to use are still very relevant, very important. All algorithms, all programs tend to be full of this kind of traps, you might say. Same again with quantum computing. So now some comparison. How do these vector supercomputers and massively parallel computers compare? So first of all, in vectors, the parallels only in arithmetic, not in logic. They were pipelines for multiplication, addition, combination of the two. In commodity processor base, you have basically full processors at every parallel node. In vector supercomputer, we have a single common memory that basically has uniform memory access time, often quite fast. In reality, of course, basically it was stacked and so on. But the idea is that every memory element is equally far away from the processor. In parallel computers, no longer the case. And somehow, in the end, turned out that in the algorithms that we were doing the weather forecasting, the furthest distance was always determining the speed. You necessarily have global data access for that. You can imagine the weather itself like being that way, but of course there's like a delay. You know, the weather in the Pacific doesn't necessarily impact us immediately. But the way we calculate it using a spectral basis, spherical harmonics, artificially couples it and speeds up otherwise the computation so fast that we can't afford to lose it. So we have in one case like fixed size, uniformly fast access. We limit it by vectorizable arithmetic in the code. In the other case, unlimited and scalable in principle, but having a speed limit. The speed limit at the time was called Hockney's. Roger Hockney, who was a British computer scientist and physicist, noticed that when you have a big scale problem and with infinite parallelism, we ended up studying actually infinite numbers of processors and how do they, in various topologies like grid-like or hypercube-like topologies, propagate. You come to a situation where you realize that there's a speed limit, which is the amount of computation capacity versus the communication capacity. And that was getting worse and worse the larger machines grow. Again, I can see something similar in tiny qubits. Harder it gets, the harder the bigger the system is, and somehow there was an inherent limit you couldn't break. Then this decade now we are back to 2020s, and we have still analogs. GPUs, the graphics processors, CUDA, and so on are now analogs of vector processors, and cloud computing has become the analog of massively parallel processors. Here I want to point out to this term Turing complete. The Turing complete basically means that it's a computational universal engine, a processor that can do in principle anything any computer can do. Now then, another development that has a bearing in this. At the same time, we thought always we are solving a mathematical equation with a unique solution. You know, the weather model is a differential equation, and you, in principle, want to have a unique solution to that. However, we observe two different things. Superlinear speed. The bigger your computer, the finer resolution you make out of it, and you actually get more and more speed, potential speed. So the parallel part of the application increases with the size of the computer you can compute it in. So we're seeing something similar to what Antti was referring in lunch discussion, that all of a sudden the algorithm started going faster and faster compared to what you expected. But we also needed this bitwise reproducibility, because we realized we've got to debug something that runs on thousands of independent processors, and then we sum it up like into some numbers. In order to know if algorithms right, we needed to be able to know every single bit that this is correct. We were able to impose it in a sort of ingenious way, this bitwise reproducibility. But it's not in the nature of the problem. In fact, at the same time, ensemble forecasting was growing fast in popularity, and that was imposing randomness, simply because we realized that what we are looking at and what we try to understand is not individual numbers or even individual fields, but it's distributions. Parameterized distribution which have the uncertainty like shrouding them. So you have a solution which is like the median of your estimate, and around that you have a cluster of possible futures. And this is how weather forecasting nowadays works. And with this ensemble forecasting, we now often are a millionfold speed up compared to the early times. Now we finally come to quantum computing. So, having the same kind of structures, we have deterministic quantum computing and stochastic quantum computing. In this case, I must pardon if some technical terms are not totally kosher, but anyway, D-wave and other like quantum annealing-based computers. So in deterministic quantum computing, we are limited by our ability to create an entangled Hamiltonian that solves that problem. And here we have quantum gates and so on, so how we reconstruct those. And we have a single common memory that is replaced with the superposition of some Bose-Einstein condensate, entangled qubits, and which is basically instant. So your memory size is limited by the degree of cubic entanglement, like heading 454 in case of IQM, now at 5 or 20, and your speed up is limited by the share of your problem that is amenable to this kind of a solution with a single Hamiltonian. In stochastic computing, we have like a global minimization problem, which is not so strict in that sense. So there the limit becomes again from information aggregation required from these different instances. That is a similar speed. Parallelism Turing complete as far as I can see in both cases. So all quantum computers in principle are universal computers. And in entangled case, we have this infinitely fast superposition. That's how theory goes. In practice, of course, it is so. And there's one point of view that I want to from theory. You know, we believe at the moment that time, the arrow of time is related to entropy gradients in the universe. So by forcing our computations to superconducting temperatures, we are basically getting them to a condition which is like, you know, the East depth of the universe. It's like time is stopping, time is ending. And we have everything in a single time instant at the same time. So it's like an analogous mental model. Whereas in stochastic quantum computing, we are still limited by the speed of light in this Hockney sense, the aggregation of the data that is needed. So entanglement is kind of opposite to this independence, you know, complete lack of interdependence that was key to parallelization, both in vector space and computers. So why are we in this kind of paradox that current quantum computers, they are maximally interdependent, and yet we know that for large-scale problems they should be totally independent of each. And in practice, many discussions today, both Mikael and Mortens refer to this problem of error propagation in that, and then error correction on the so on. So in practice, we are having in a stochastic computational mode that we have to repeat many times in order to be sure that we get the right result. So why not use the option? And now we come to photonics and so on. Instead of this, why don't we get our parallelism out of coherent photonics? And here I'm literally like speculating really on a possible other technology that may already be practiced by some others. So I'm not aware of that, but I just thought that this could be like a potentially worthwhile idea to do. Because we can digitally create coherent white light with diffraction grating of very many different wavelengths in parallel that will not interfere. They are orthogonal because they are coherent. So you get into the same fiber sent white light, which when it's coherent will not interfere. Every color will come out beautifully separate, if I now understand what you're talking about, right? How physics seems to tell us. So we can actually have any number of parallel inputs into the same optical pipeline, only limited by how many different wavelengths we can generate by diffractive optics. So what is the problem? Like in superposition, Hamiltonian defines the computable optimization problem in this entangled quantum computing. Here we have an algorithm that can actually calculate not infinitely fast, but at the speed of light, literally at the speed of light. However, the challenge comes from the programming. The programming is actually a sequence of lenses and prisms and so on. And those we would need to form into optical gates or photonics gates that would be analogous to quantum gates, but probably different simply because the physical framework is different. But they should also be able to provide passively a Turing-complete set of operators, binary operators. This is something that I have no idea, or there's no full understanding at all at the moment if that is doable. And therefore, because of lack of this interference, we suddenly have a deterministic optical quantum computer. It produces the same result every time, no randomness, none whatsoever. But it's such an optical quantum computer. And now here, my final speculation. Maybe, and I'm sure that we'll end up studying this with Elvis and with Jyrki and Andreas and others. So I invite the Joensuu photonics people here so as to we can share these ideas and maybe go further. So this comparison, entangled quantum computing, we typically use fermions. There are photonics-based indeed versions, and spin is part of that. It's infinitely fast in principle by superposition, entanglement of spinning qubits, for example, and superconducting layers to maintain entanglement. Logic by quantum gates. Parallelism by entangling many qubits, so that superposition covers all possible results of the computation. Schrödinger's cats in more mundane disguise. And the output is by really repeated stochastic resonance. But in coherent quantum computing, that would be bosons, speed of light. Coherence and geometric phase. And geometric phase is interesting because we can have the dynamical phase, which is the phase of the wave, plus polarization, something that Elvis Billiman here has been studying intensively with Kauranne. So it's really great that you were able to come here. And it's young double slit experiment and the wave particle duality aspects of quantum mechanics that come into play here. Can be done in room temperature, ambient temperature, logic by convolving diffractively graded lenses, for example, double slits. So this is, I actually believe that this double slit experiment may become key to this Turing completeness of this. Parallelism by coherent techniques. We can have thousands, if not tens of thousands of wavelengths and feed in many inputs to the same algorithm simultaneously, get the result, the speed of light. Output is retrieved and also intermediate inputs on photosensitive screen or lenses. So just pass the light on and read the end, and you get it like on a photograph, plate, and that's it. The challenge is the programmability, because right now the program is actually engraving digital lenses. And you don't do that in software very fast. So it seems to me that maybe something that might emerge from this would be something like FPGA type of thing, programmable gate arrays, like templates for embedded processors that initially calculate only a single algorithm, but very fast and very many inputs. And that's all I have to say today. Thank you very much. Maybe there will not really be time for questions, but if any emerge, I'll be happy to answer.
Yes, thank you, Tuomo, so much, so interesting. Any questions to Tuomo? There is one.
Tuomo, I just have a comment that I guess you're picturing like an array of linear optics and lasers, and then just measuring the intensity of light.
And the phase, remember, it's coherent.
And the phase, right. Unfortunately, that does not give any quantum advantage. That is already proven in the literature. You need to have either nonlinear elements, single photon sources, or single photon detectors. That is something that is already known.
Yes. But we do get this parallelism, remember from.
Yes, but but it is classically computable easily. I mean, that does not give any quantum advantage. What you're saying.
No, it gives a massive speed up. That I can guarantee you.
Maybe there could be some speed up, but it's basically not a quantum computer.
Yeah. Okay. Fair enough.
Very good. There is another question too, please.
Yeah.
Just a minute, you will get.
Mikko, sorry, I didn't get this to you, but you had a very loud and nice voice.
Hi.
Can you hear this? No.
It doesn't work.
It doesn't work.
Yeah. Anyway, comment as well for that one. The idea of being able to get coherent light through any kind of cable, and that's in a perfect world. We already have to do like an unpacking of the wavefront in a longer transportation over the sea cables, which is basically us knowing the error in the cable or the fiber, and calculating backwards from the wavefront that actually happens regardless we are trying to use a coherent light.
Yeah.
So that's there. I know that there is some amount of research done in China regarding like using this kind of a wavefront on trying to get a quantum computational advantage out of it. But as said, it doesn't seem very promising. We would need the single photon source, which we would actually have expertise in Joensuu to do that. There's a long project done with Aalto University on that front, but that gets us to the biggest problem, which is photons are really, really good staying coherent because nothing affects them. And in order us to get to an entanglement, they would need to communicate, and they hate doing that.
We did talk about entanglement actually. I was talking about the German classical computer, remember? And we do use single photon lasers all the time in our remote sensing activities. We have Geiger mode and we have single photon laser, but 2 vendors. So that's a link. But yes, the guy next to you will be able to say a lot more about this. So we'll come
But thank you. Let's move on the program so that we have time for all the speakers. And the next one is, of course, very, very interesting. PhD Dr. Mikael Johansson from SCS. And he's a quantum CSC. And he's a quantum strategist and CSC is an IT Center for Science, and also they have built the LUMI computer, which is a little bit north from Joensuu here, and it's the fastest computer in Europe. And what they also made titles in international press, what they connected LUMI computer with the IQM computer. I think it was IQM computer, Mikko. Yes. So this has made some notifications in the press. So it's going to be very interesting to hear, Mikael, what you have to say. So please, the stage is yours, and give us your best.
Thank you, Christina, and thanks to Olli for inviting me here. I must say I'm very happy to be here at the Quantum Karelia closing event, not because it's closing, but let's actually hope it continues. I must say that during the 2 years I've been involved here, it has really provided a rather unique forum for discussion between, I said somewhere between the quantum curious and the quantum experts, and in the same room, and then really kept the discussion going and looking at different viewpoints. That one maybe doesn't get in a purely expert setting, let's say like this. Okay, I'm going to look a bit at what we can, in our view at CSC, do with quantum computers. And our business for 50 years has been high performance computing. And is there any pointer here? No one else shut it off.
Okay.
But yeah, but anyway, so the story of CSC started in 1971, but actually it's a couple of years earlier than that. The process that put everything in motion happened because the Bank of Finland in 1969 noticed that they had 20 million marks that they had to get rid of. There was a surplus that they had to do something with. And the task was then given to, you should look up the details on properly on the net is available, but in short, it ended up with a task force sitting in a sauna that had the task of bringing Finnish science to the next quantum level. So that ties nicely into the discussion here also. And after considering various propositions like some new paper mills or paper factories or something of how to bring Finland to the Finnish science to the next quantum level, someone in the summit shouted out, "Let's buy a supercomputer." And then everyone agreed, "Oh yes, this is a great idea." And that's how the UNIVAC 1108 came to Finland. And also the beginning, in a way, of CSC. We have grown a bit from that, so now we are almost 600 employees, and we do much more than just supercomputing. But for the purpose of today's presentation, the HPC part is the relevant. But in principle, or not in principle, but in practice, we do much more these days. Okay. I want to start with this definition of what a quantum computer is. It's rather simple definition, but it's good to keep in mind. So a quantum computer is a device that directly exploits quantum mechanical phenomena in order to perform a calculation. And these quantum mechanical phenomena are the usual ones of proposition, entanglement, and wave function phase. But I emphasize directly here because already in the present day CPUs and GPUs, there's lots of quantum phenomena going on, of course, but usually those are seen as a nuisance that actually disturb the computing. But in a quantum computer, the idea is to really use these basic natural phenomena and use them to do a computation. At the same time, you should remember what a quantum computer is not. So quantum computer, it was already mentioned a couple of times in the previous talks, but a quantum computer is not a super fast version of a classical computer. It's a completely different creature. And the implication of this is that it really does have the potential to speed up some types of calculations, but for most types of calculations, it actually just cracked. But we need to focus on this. The application fields where a quantum computer actually can give some advantage, measured by different means. Okay. So as mentioned, quantum computers really can be super powerful for some tasks, but they will always need a connection or cooperation with the classical computer, because they will not be able to do everything. Even your laptop does. They are not suited as a general computing device, even if they are, as Tuomo mentioned, so they are more than Turing complete, but it's not efficient to use them for adding 1 + 1. But also we should know that quantum computers are already more powerful than supercomputers for some tasks. So far they're not faster for anything useful, but for actually getting to do something useful, we need higher quality qubits. But that's coming. And the belief in quantum computing is actually surprisingly high, I must say, for in my personal opinion, for a technology that still is very emergent. So all the major nations and larger ICT companies are involved here. So you of course know that IBM, Google, Alibaba, Amazon, Microsoft, so forth are heavily investing in quantum computing. In Europe it's different, and mostly due to a lack of really large ICT companies. So in Europe everything is startup driven, which has its positive aspects, but also challenging aspects. But that's not part of today. But the largest general purpose quantum computer so far, largest counted by qubit count, is the IBM Osprey that has 400 qubits. And for the moment, both IBM and Google estimate industrially relevant quantum computing by the end of the decade. I think this is where we are now. Just want to have a small slide in between about the quantum computers being faster. So this was innovation in 2019 by Google and later also by the Chinese optical quantum computers that were mentioned a moment ago. But so they can already do calculations that supercomputers cannot do. But the problem is that because of noise and imprecise control, the quantum computers crash very quickly. So, and this is the reason why there's not time to do a useful calculation before the computer crashes. And car analogies are always good. So we can think of quantum computers like being the fastest racing cars that have ever been built. But they are modern racing cars, so they are electric, of course. But we can think of it that the battery runs empty after driving for a few meters. Also, the steering wheel falls off after you turn right and left a couple of times. This is, of course, not a very good racing car. You want to drive several times around the same lap, and not just a few meters. But during these few meters, they really run faster than anything ever seen. So now the next step is just a matter of improving the batteries and then also installing better steering. And that's an engineering problem that is steadily going on, as we heard from Mikael the other day. And at the same time, the horsepower of this turbocharged quantum engine keeps growing all the time. Okay, what happens next? Next, quantum computers, and this is already happening now in a way, quantum computers will merge with supercomputers because the more powerful your quantum computer is, the more powerful actually also the classical counterpart needs to be to balance up the computational power that you get from a quantum computer. And classical HPC is needed for many different things. And one part is those parts of, if you have any sort of real world workflow, computational workflow, much of that will always need supercomputers to be solved. So HPC and a supercomputer is needed for those parts that will never efficiently be run on a quantum computer. And practically all real-world problems have these parts. They will also be needed for controlling and orchestrating parallel quantum computing. We'll not get into that more, but error mitigation and correction was mentioned already, but error mitigation of when you have a very noisy output, then you really need some massive classical computing power to really analyze the data that you have and get out something that isn't just white noise. And another interesting aspect to me personally is this, that the programming quantum computers is very difficult, and there's already lots of efforts in trying to build artificial intelligence programs or machine learning programs that actually do the programming for you. And also compiling for quantum computers, because as mentioned, so you really need to have very short programs for them to be able to finish before the computer crashes, and to really optimize this so that you get as short a program as possible. Then you also will need classical power, especially when you grow in qubit count. Now when we have 5 to 50 or 100 qubits, or 400 even, you can still do that rather easily on a well, maybe not for 400 anymore, but you can do it on a laptop. But when we get to meaningful qubit counts, then already just compiling the program becomes an HPC problem. And I just mentioned here a couple of the application fields for where we combine HPC and QC and well, the quantum computing. For artificial intelligence is one of the major ones mentioned often, but we should also mention and remember that using AI for quantum computing and quantum technology in general. Then there's the financial applications. Financial applications are usually, and financial institutions are very keen on jumping on new technology because they're, of course, even a tiny advantage in speed or accuracy translates into big dollars. So you don't need this exponential speed up. If your risk of your investment portfolio drops by 1%, you're very, very happy. Optimization and logistics problem in general, but then also you'll hear more next about electronic structure problems like material science, chemistry, and pharma is very high on the list. And the future will also change the focus of quantum computing from the hardware to software, and software will become dominant because it is with software that you actually get something done. So just as in classical IT and classical computer, so the big money lies in the use cases and the software. So Intel is big, but Google is going much bigger. So there will be a shift towards the software. Okay, some challenges and differences to someone who is used to using classical supercomputers is that the first one is of course that what should quantum computers actually compute? This is not at all a trivial question, and it's very difficult to answer. And then we really need to program them in a completely different way. So we have to rethink the problems. Instead of just trying to solve the same problem that you're running on a classical computer, you really need to think from the beginning, what is it actually that I want to solve? So should I now just try to change my program so that this one matrix diagonalization can be run on a quantum computer, or should I actually think of why am I doing this matrix diagonalization? And I think that for the really breakthrough applications, then you really need to not just try to translate your existing programs, models, approximations to your modeling problem. The quantum computer, you really need to, from the beginning, think of what are you actually solving, and then think of, can we do this in a different way from classical computers? And then, for a very long time, you need to work around these limitations that were mentioned, the noise, qubit connectivity, decoherence. Fault-tolerant quantum computers will come at some point, but that future might be very far away, and we should not wait for that to come. We need to already take into account that our programs have to be aware of that the quantum computers will compute wrong most of the time. Also, no quantum computer is the same, so they are all different, which means that the same program will produce different results on different hardware. It will also produce different results on the same hardware, but different quantum computers are suitable for different things. This means that from an end user perspective, we really need access to several different quantum computers, because some problems will be very suitable for superconducting qubits, others most likely will then be suited better for ion traps and so forth. And as Mikael mentioned also, this co-design of designing your QPU so it fits a specific problem will have a big effect on performance. So you, as an end user, to try out what you are trying to develop, you need access to several quantum computers. I just want to mention here, FIXIT, the Finnish quantum computing infrastructure. It's on the Academy of Finland roadmap, FIDE roadmap, and it's a cooperation between VTT, Aalto, and CSC. And here we want to really provide to the Finnish community state-of-the-art quantum computing services. And the pilot phase for accessing HELMI, which is the VTT IQM quantum computer, is now open, and all academic users in Finland can apply for a project, and then you get access to a real quantum computer. A bit more about that later. But the fonts are not included here. So okay. Anyway, brief slide of what has been done with LUMI so far. So earlier this year in March, we actually connected LUMI with a Cal 9000, owned by Jarmo's quantum computer in Sweden, and run what probably was the first cross-border quantum job where we were combining a supercomputer and a quantum computer in two different countries. In May, we did the same with the VTT IQM HELMI quantum computer, and then we integrated it into the supercomputing environment with identity management and resource allocation and all of this. And next, what we want to do is to implement the LUMI Q concept, which really means setting up a global distributed HPC plus NQC, which signifies that we will have several quantum computers. We will start from Europe, but the idea is to really build up a global network of these. And this requires developing software stack for this, which is the major part of the work here. But the first stage in LUMI Cube, funded by the EuroHPC joint undertaking, combines several countries working together on this, and in the first phase already we will connect several quantum computers. So we have Helmi here at VTT, and then we have Jarmo's computer that are already very connected. But then we also have the quantum computers in the Netherlands, and then we will buy another computer that goes to the Czech Republic, Czechia. And the idea here is to really, from the beginning, get several quantum computers available to users throughout Europe, and this will be available to everyone in Europe, including companies. Just like the LUMI supercomputer is for the moment. So that is also available to all users in the European Union, and 20% of that is reserved for industry. Okay, mentioned here that the pilot phase opened, and really everyone here should apply. You need to explain a bit what you want to do with it, but it doesn't have to be high science. It's sufficient that you are curious of what to do with it. And I think one great thing that everyone here in the audience should do already is to, as Mikael mentioned before, just create an entangled Bell state and do an experiment that won Nobel Prize this year. And now you can do that from your laptop through this. And that's actually, in a way, I think that's rather fantastic. And it's really based on a purely Finnish technology, the VTT IQM quantum computer that you can control now and really do, not in a way a computation. The computation part is not the important part, but really to create a quantum state from your laptop that is of such a fundamental importance for science that 3 people got the Nobel Prize this year. And there's very few Nobel Prizes that you actually can perform from your laptop. And well, as Christina mentioned, so this was also noted abroad, and my personal favorite is the piece in the register. I've been reading that for a long time, and they are usually very, very nasty, but not very nasty, but they have a nasty edge to them. But this one was actually very, very positive. And I actually like the interest there. It's not how many qubits you got, it's how you use them that is important. So, which brings us to this question. So what can you do when you have 5 qubits? But now the emphasis is on 5 real qubits. So we can run any calculation in principle that a 5 qubit quantum computer can do on your laptop, but that's not the important part. When you have real qubits, they will be completely different from anything that you can simulate or emulate. Here the important part is that they actually will not behave ideally. So you really, by using a 5 qubit quantum computer, you learn how to use real quantum computers. And again, a bit repeating what was said earlier, reiterating, so they are very different from traditional computers. So you really need to program them in a completely different way. They differ from each other, and the quantum computers really do compute wrong most of the time. And this is a very different thinking now needed for people who are used to doing some sort of supercomputing or simulations, that coming away from this feeling that you should get reproducible answers like Tuomo was telling here. So that is a comfortable thing about supercomputers, and any classical computer, that if your laptop computes wrong during its lifetime before it breaks, then you bring it back to the shop and say that this is broken. And as mentioned, a quantum computer crashes in some microseconds and computes wrong almost all the time. But they are still useful. That's the point here. And for someone who's doing simulations of computers, it's really a different way of thinking, because a quantum computer is really a device for experiments. You are setting up a physics experiment, even if you are having your algorithm as a circuit, but it's just a recipe of what experiment to run on your quantum computer. And then you will get your error bars and everything that you're, maybe at least me personally, when I got into computing, it's something that you really wanted to avoid, the uncertainty of experiments and measurement devices. But now you have to start thinking of that again. And one also needs to be, due to the experimental nature of this, one has to be critical to the results in a completely different way than one used to. So if the computer says something ridiculous, it probably is ridiculous, and it's not just cool new science and you discover something super cool. But you have to be critical to what the results are in a completely new way that you didn't really have to do with classical. So maybe you had some wrong input parameters in your file or whatever, but that produced really ridiculous results. But now you really can get wrong results just because, well, the tram happened to pass by the quantum computer when it was doing its calculation. But this also means that you really need to get this feel for how to use a quantum computer. You can only get this by using a real quantum computer. You will never get this from using an emulator or simulator. Partially, you can get a feel for how a quantum computer works through an emulator, but to really get this hands-on knowledge of how should I run a program in a quantum computer, you need to do the experiment yourself on a real device for experiments. I would finish here that the quantum advantage, no matter how you define it, if you want to define it as getting results faster or getting results using less energy or just getting better results. So getting to this ultimate goal that we are still not there, but this is really a multidisciplinary problem. And solving this problem really requires crosstalk between all sorts of fields, because otherwise you will implement something that actually doesn't really work in real life. So you need to have experts on solving whatever problem you're solving on classical HPC, because you need to have some sort of benchmark that you're trying to beat. Then you need to have quantum computing experts, but also quantum computer experts. So you really need to have people who understand how your computing device is working, which is something that you don't need in HPC. You don't need to know how your Intel or AMD processor works. It just works. But for a long time here in quantum computing, you really need to have constant dialogue with someone who understands the computer itself. And also, you really need to, from the beginning, talk with end users. You need to know what you are solving and what you want to solve for. So you need to have experts in the actual domain that you're writing a program for, so that you're not just writing something that you think is cool, but will actually not be useful. And but by combining all of this, then really, even before we get to fault-tolerant, noise-free, or error-corrected quantum computers, we really can get quantum advantage. And my feel is that this is where the emphasis, not only in the near term, but even, let's say, 10, 20 years should be put, because it will take a long time before quantum computers become so reliable that they are as reliable as classical computers. And here, I think that also the HPC infrastructure and HPC centers really provide this common platform for collaboration where we can get all of these experts at the same table discussing things. So these images are created by this DALI 2 text to image AI engine, which is actually quite fantastic already at this stage, even if it doesn't use any quantum computing, but we can think of what it will do connected to quantum computers. But this is just Linux experts trying to solve a problem of quantum computing, and this is what came out. Okay. with this, I think it's time to stop. Thank you.
Thank you so much, Mikael. Any questions to Mikael? Okay, I have a question. I've been listening to Sabine Hosfelder, who is doubtful about quantum computers, and she has very nice lectures on YouTube, which are very humorous and also informative. And she's saying that one problem with quantum computers is that there is a lack of algorithms that could then make the computer to make or fulfill its promises. So is there enough algorithms?
No, definitely that is a problem, and that's where efforts really need to be put now. So actually come up with ways of using a quantum computer in an efficient way.
Okay.
So I think that she's definitely right there, but it just means that you need to put more effort into software development and to balance the hardware development.
Yes, and not let the quantum algorithm professionals move out of from Finland, but keep them here and help our quantum providers, perhaps.
Yes. But at the same time, the whole problem is very global, and we need to collaborate. So from a global perspective, it doesn't, of course, matter where the people are doing this work, but from a local Finnish perspective, it would, of course, be nice if they would be here and create a new Nokia.
Yes, absolutely. That is what we are hoping for, new Nokia. Thank you for reminding us. But thank you, Mikael. Fantastic presentation and so informative. So we are moving on with our program, and our next speaker is Antti Poso, who is working at the UEF, the University of Eastern Finland School of Pharmacy, and the University of Tübingen. He's a professor, and he wants to say, just to mention that I'm not a quantum computing specialist, but I know something about drug discovery. And based on our discussion yesterday, so I can say that Antti is also a fact checker. He, when our discussion goes like mopo keuli, so he's the one who is saying that, okay, stop now, let's see what is the reality. And so good to have you here, Antti, please.
Thank you very much. And honestly, I'm really not sure why I'm here. Because the fact is that I really don't know anything about quantum computing. Why? I never use it. I'm going to use it when I see that there is a benefit, which is mentioned already here during this presentation. There must be a benefit. Scientist is not doing, well, most of the, well, at least sometimes we are not doing something just because we want to try something, but we want to have some benefit. And the benefit in case of drug discovery is really that we can find new compounds to be used as drugs. The problem is that designing new compounds is not, well, there's two terms. We are speaking about science or scientia, and we are speaking about art or art. And if you now would think about, let's say, building a bridge, that's something like construction and not simulating, but modeling the system. And you get a perfect result by using AutoCAD and some physics and so on. And you can tell most of the time if the bridge is going to be stable or not, except in Turku, where that's a different story. But the point is, you can think about that the bridge will still stay there and everything fine. And if you are designing an airplane is flying perfectly fine, unless it's used by Microsoft software, then it's a different story. But again, the point is you can really be sure what you get. Now, if you go to the chemistry and not discussing about discovery, but chemistry, synthesizing new compounds, that's not anymore science in that sense. We have to actually try first, second, third, fourth, fifth, seventh route. We don't have an algorithm, we don't have a science, we don't have enough knowledge just to tell that if we have a two compound, one acid, for example, and an amine, and then we put those together, that automatically we know exactly what's going to happen there. We know 95% of the cases, But sometimes we just don't get things happening. And sometimes, most of the time, it's a science, it's a gut feeling of a scientist what we get out there. Now, because of this, I actually think quantum computing is something which is going to make a big positive impact for drug discovery in future, because we are now forced to stop trusting our computers. People are trusting computers and simulations in drug discovery, like, you know, in Finnish I usually say that looks like katselee kuin sammakko putkimiestä. You know, looking like a frog is watching a plumber, you know. Whoa. So that miracle on the screen, and we believe that one, and that's not true. So the point here is very simple. We think that we have an excellent algorithm which can make a golden eggs, or actually at least some kind of eggs out from chunk if we put that into the algorithm. But this image actually gives one good analogy to quantum computing. And this analogy is that, or any honest computing, is that you get a little bit different outcome here, depending what you put here, but you really have to be sure that this part is well behaving and well fed and well, you know, taken care. You don't get something out here. Well, instead of simulating chicken, in drug discovery, what we are simulating is chemistry in biological context. And now I told that we cannot design, or we cannot predict 100% certainty how this individual synthesis of a compound is going to work. Then how you think we could design or predict which compound would biologically make sense in a certain process? It's totally impossible. And yet we are doing that one. And we are doing that in the same aspect as chemistry, that meaning that we are doing round and round and round again and learning from trial and error. And the trial and error in drug discovery, in old-fashioned computer science, what you can see based on the screen type here, is the following. We have a protein target. Most of the drug molecules are hitting a protein inside human body, and they are interacting with that protein. When they are interacting with the protein, they are doing some biological effect. They are shutting down the protein activity. They are activating the protein. They are preventing two proteins to interact with each other, whatever. But they are doing something into the biological context throughout interacting with the protein. And what we do, we try to invent a compound which goes here by using computer screening or literature search or whatever. And at the end, we have a certain number of compounds we want to use as a starting point for the drug discovery project. This is a screening problem. And the screening, what's done here is, for example, filling up a database of 1.5 billion compounds and going through those with a computer algorithm one by one, and then testing 100 best by synthesizing those 100 best and then checking which one is working. Once we get something to work, then using different type of computing methods, we can calculate the initial, the compound, which is never good compound. The first compound is always bad compound. It's totally useless compound, but it's a good starting point for the drug discovery. Then we optimize a compound by first looking what we can do there computationally. So what type of modifications we can make. And once those modifications are really designed, then actually we synthesize a compound and then we test. And then we actually measure in real life using crystallography or NMR or cryo-electron microscopy. We measure actually how the compounds are binding there. And then we put all of that back into the computer and design the next round of compound, the next round of compound, and so on. So instead of directly designing a new compound, we just do designing of 100,000 or 10,000 compounds and testing all of those. And at the end, we take the compound, let's say 2, 3, 4, 5 compound series, which we take to the clinic, and with the good luck, once those are actually used, and that's it. Now, from the computational point of view, what are the chances, if we think about this computational drug discovery, computational chemistry, what people have been thinking, where the quantum computing could work. There's a pretty newspaper, the article Matter Theory, published earlier this year, which claims that there are some fields where quantum computing might work. I don't agree with all of those, and I can tell that some of those methods are totally out of reach from the real drug discovery business. However, there are some things which I can already now tell we can really work. First, molecular structure prediction exploration. Quantum computing is probably a good method to predict the structure of single chemical compound or protein and so on. However, that is not the rate-limiting step in most of the part of the problems what we have. The second thing where we can really do is the biochemical processes, for example, drug molecule protein docking. But here, currently, the main problem is actually not the computing power, but the quality of our current predictions. Why? Our current predictions are a type of politicians. It's you ask one politician, is this good or bad? And the politician tells, this is good, this is bad, this is good, and this is bad. And if you trust that one, then you are like a first-year student who looks at the computer and says, yeah, the computer tells that that compound is good. Yeah, computer tells, but it has nothing to do with the reality. The same as you ask a politician. Now, if you ask from 25 politicians, and 19 of those tell it's good, and the rest tells it's bad, you might think it's good or bad. But if you just take one random, well, that's it. You can think about one random Finnish or American politician, and if you can trust that person, it's up to you. But the point is, quantum computing actually is good in that sense that it brings us back to the idea that we cannot trust the computing results. People are trusting the normal computing results, but we should not, because the current methods are unable to predict the drug binding or docking properly, because the interactions are too complicated to be calculated by any rational means. So there are too many simplifications which are losing all the data which is relevant, and we even don't know all the relevant data. Here's a good example. We have two compounds here. Both are predicted to be perfectly fitting. And we know they fit. And if you can tell me by any means that which one is better or worse, I can hire you if you can do that always right way. The point here is the difference between these two compounds binding in the same binding site is 3 orders of magnitude. And the funny thing here is that the one where we have a more interaction, so these dashed lines are strong attractive interactions here, and here the dashed lines. This has much higher, or let's say stronger interaction, and yet this one is more potent. And you cannot predict that with any single calculation, even with quantum mechanics, not quantum computing, but quantum mechanical calculations. Because even quantum mechanics is not taking into account the aspects which are needed to explain the difference in biological activity. And that means that even if we can use quantum computing to calculate quantum mechanical structures, it's not going to reveal the data what we need. What data then we need? We need this. This is a compound we designed in Germany. This is in Finnish compound. This is a suomilide. This is a macrobial compound coming from natural sources from somewhere Gulf of Finland, or somewhere in Finland. Who cares where? Some of the slimy things coming out there, and it's capable of interacting with one biological process, one trypsin type enzyme, and blocking the activity of that enzyme. Now, each of these single frames, what we are looking, this is 2 microsecond simulation. This simulation we need, but we don't need 2 microseconds. We took about 1 week to calculate with MAHTI supercomputer. We need 250 microseconds to 1 millisecond per compound for 100,000 compounds to be calculated. We want to predict which one is going to work and which one is not going to work. And if you can give a computer which can calculate that, and the problem is these are not random, this is like a movie. And the problem with the movie is, if you don't know when the movie starts and when the movie ends, when you know if you have enough simulation? Here is a very simple thing. This is a movie, the same movie, but with different length. And then the movie continues, and the movie continues. This takes maybe 1 day, this takes maybe 1 week, this takes maybe 5 weeks, this takes 10 weeks to calculate. And if you look these values, you really don't see that. Okay, you think this is stable, this is enough, but it's not stable. You have to calculate more, you have to calculate more, and you have to calculate more. And the simulations, what we have to do are really this type of things. We are wandering in the dark, and we have to find out what are when we have simulated enough. And in this particular case, we simulated enough because we simulated KRAS protein, and then we were able to do an analysis, which are the relevant, the most important frames of the movie, which can then turn back into the biological activity. Okay. To end, about quantum computing and drug design. Time matters. We must simulate things what happen in time. And there are a lot of problems what must be included here, a lot of aspects, but the simulation is needed here, not just a single calculation. We have to simulate the whole system. And why these systems are so big? Think about if you are having an interest about endocannabinoids. I don't know why, but maybe you might have interest in endocannabinoids. You want to design a compound which blocks the endocannabinoid system. That means you have to simulate the receptor in the cell membrane, having a different type of cell types, different type of solvents. The system size is easily 5 to 10 million atoms. Then you have to simulate that one for 1 millisecond time. And you have to calculate the time steps, which are 1 to 5 to 20 seconds per step. Challenge for you. Another thing which I want to underline here is that ultra-light libraries is an easy topic which we could already now start to think about using the quantum computing. Current screening libraries are big. The biggest ones currently are 20 billion compound. However, the biggest one which we know is really calculated in 3D shapes is 1.5 billion compounds. We did that with Mach supercomputer using a little CPU, some electricity, and heated half of the Kauranne with that one. But the point is, it's still the largest library in the world. And we only scratched the tiny surface of the chemical space what we can use in the screen. So just to build up the libraries might be a good thing. The screening of this database, taking individual compounds and using docking or whatever simulation, not simulation, but scoring methods, might be also another thing for quantum computing. Because screening for these 1.5 billion compounds against one single target takes basically 2 months, 1,000 CPUs, 24/7. Okay, but that's all. The rest you can read here. There are some usual suspects which are mentioned here, and if you have any questions, I try to give an average answer. Thank you.
Thank you, Antti, so much. There is time for one very, very short question. We are late in our schedule. I just noticed that.
It's not your
It's not your fault.
It's combined work.
It's my fault because I didn't stop the interesting talks. But thank you, Antti, so much. And I look forward to talking to you again about facts. Yes, so we are moving forward, and thank you, Jagadeesh Pusapadi in Amazon Web Services, that you have been waiting and you are still available to talk to us. Amazon Web Services has been a friend of Kvantti Karelia since its beginning. Hello, Raisa Haapala out there. Nice to have you in our audience. And hello, and Jagadeesh has been so friendly with us that we call you Jags. So welcome, Jags. You are in London now, and you work with quantum computing initiatives at AWS. So please, Jags, the floor is yours, the virtual floor.
Thank you. It's really nice to be here and talk to you all. I'll try to keep it short. Just want to confirm you can still hear me okay? There's no noise?
Yes.
Yeah, perfect. Thank you. So I am one of the solutions architects based in the UK, and we've been working with the Quantum Karelia team for over a year now, and it's been interesting. We have run some few workshops. Today, I'm going to give a quick update on different initiatives AWS has within the quantum ecosystem. So Amazon Bracket is the service which is quantum computing as a service. We'll talk about that in a bit more depth. We also have a Quantum Solutions Lab, which is helping customers and other research institutions build solutions that are with using quantum and other HPC and machine learning solutions. You also have a vibrant partner network who are building on Bracket. And importantly, we also have 2 research and development initiatives. One is Center for Quantum Computing. This is, and the other is Center for Quantum Networking. So I'll talk about these 2 initially, and then jump into other parts, and then we'll do a bit more deeper dive on Bracket today. So AWS Center for Quantum Computing is based out of Pasadena. It's a joint collaboration with Caltech, and we have many researchers and engineers working on building a fault-tolerant quantum computer and developing new algorithms as well. So last year, our CQC published a paper on theoretical analysis of a new architecture to build a fault-tolerant quantum architecture. This is kind of needed, as everyone has talked about so far. In today's world, we don't have a practical, useful quantum computer. Today's quantum computers are mainly used to learn about quantum computers and get ready for when we have these useful hardware where we can run actually useful applications. The technology we are focusing on for Amazon's quantum computer at CQC is superconducting based. And we have set out, so we already built few chips, but none of them have been released or made available yet because we want to focus on a practical quantum computer. So what are the key criteria that need to be met? So from our side, we want to be able to support at least 100 logical qubits and more than that. So a logical qubit is error corrected, error free. Depending on the technology used and different aspects, that can vary from one logical qubit may need maybe tens of physical qubits or maybe thousands. That bit is still kind of unknown. We also want to be able to support a universal set of gate operations between these qubits and also run an error-free circuit operation for a larger circuit depth, i.e. multiple gate operations in sequence, maybe up to 1 billion, and also run a clock rate of tens of kilohertz. So that's the aim we are looking for. So with these most demanding criteria, we are looking at error rate of 10 to the power minus 12. That's about 9 orders of magnitude beyond where the current state of the art technology is. So that's where we are. That gives you a scale of where we need to get to have any useful and practical quantum computing. Switching to another area where we have, it has not been as prevalent as quantum computing, is the quantum networking. So to unlock full potential of the quantum devices today, they eventually need to be interconnected together in a quantum network. But there are other useful, fascinating applications of quantum network. One of them is like global communications protected by quantum key distribution for improved privacy and security levels. They are not achievable using conventional encryptions. And quantum networks also will provide powerful secure communications between quantum computers. That way they can amplify the capabilities of individual quantum processes. So that's again, a promise of the future. So with the AWS Center for Quantum Networking is based out of Boston area. So it's a joint collaboration with Harvard University. So the quantum networks they use photons and entangled quantum qubits to distributed them. But as you can know, with photons and distances, these entangled qubits kind of decohere and are lost after a distance of about 100 miles. So we are working with researching around quantum repeaters, which kind of involve quantum memory, which uses which can use to extend the range of these quantum communications. We recently published a paper along with Harvard University in Science magazine. I'll share these links later on. There's a couple of blogs on that. This quantum repeater is they have achieved with a particular material which can operate at a higher temperature than like absolute zero. So this is one step towards practical quantum repeaters, and we also kind of doing some POCs and initial networkings with few of the companies. And in QTB, Horizon Quantum, they announced a small POC where in Singapore they've interconnected 2 buildings using entangled quantum network and using the QKD in there. So moving to one of these, the third one is the Quantum Solutions Lab. So this is a collaborative research engagements with different enterprises, small and medium businesses, and also research institutes. So here we have a team of experts, not just in quantum computing, but also machine learning and HPC. So the aim is to work with customers and work backward from a particular problem you're working on or an application you're working on, and build solutions, not just using quantum computing, but using all the technologies available. So it's more practical, pragmatic way of solving today's problems with available technology today, but also preparing for the future and getting the teams quantum ready. One of the use cases where our Quantum Solutions Lab work was with BMW, and they worked with this quantum challenge last year. And there was a challenge set out and a competition where they came up with some practical use cases of their day-to-day needs in the manufacturing process. And this is actually the challenge was done, and they are working through some of these solutions currently. And AWS has a large ecosystem of partners. And this is a global program. And specifically on the quantum side, we have many of these partners building their solutions on Bracket and making use of brackets features and doing all the heavy lifting, leaving the heavy lifting to bracket. That way you can build solutions that are ready to go from a customer's point of view. Right. Lastly, we'll look at bracket. So this is the quantum computing service. So this is a kind of a one-stop shop where you can kind of build solutions. You can test your algorithms in simulators and actually run them on real quantum hardware from different types of technologies, and also aggregate the results, analyze them to see, and then choose the best possible solutions for your application. So Bracket has an SDK. It's an open source Python library. We have released it in GitHub. It comes with 2 local simulators. You can get started easily by just doing a pip install. And these simulators, you can have these running locally. You don't even need an AWS account or any credentials. You can just get started. And there are many examples available on GitHub as well as part of using Bracket. And Bracket SDK has also been integrated and has plugins from other frameworks. So one is PennyLane. So this is a Python library for leading in the machine learning area. So you can use PennyLane with Bracket SDK to submit your problems across different quantum hardware providers. And as you know, Qiskit has been leading the way for some years now. So we also have a Qiskit provider for Bracket. So this was developed primarily by open source Qiskit advocate program, mentorship program, along with our Bracket team. So this allows you, so if you're already having a Qiskit program, it's easy to just switch the backend and run those Qiskit programs on a Bracket backend with, so you can run them on multiple hardware and simulators. So Bracket itself is like any other AWS service. It's built for you to get started easily. So it's all API driven. You can interact with the Bracket service by installing the SDK locally in your IDE through the AWS console. And we also provide managed Jupyter notebooks. So you can log into your account, spin up and manage notebook. It comes with all the prerequisite libraries installed and also examples and also an algorithm library, which I'll cover in a second. And you can go from there. Let's talk about some of the simulators. So we have quite a few simulators. The local simulator I talked about, which comes part of the SDK. We also have a large, like high performance managed simulators. So we have a state vector simulator, which, as the name says, it stores the whole state through the entire calculation. It supports up to 34 qubits, and we also have tensor network simulator, which analyzes the quantum circuit and encodes it into a structured graph. And this is suitable for like sparse quantum circuits, and depending on the structure of a circuit, it can support up to 50 qubits. And this does it in 2 phases. It tries to find an optimal graph, and if it can contract it, it'll go through rehearsal, and then if it finds an efficient graph traversal, then it'll do the actual contraction phase and run your circuit. And the last one is density matrix simulator. So as we know, today's quantum computers are noisy. So with density matrix simulator, you can actually simulate noise. So you can really simulate your actual hardware behavior of today's QPUs, and then see how it impacts your algorithm before even running it on a real quantum hardware. Looking at some of the quantum hardware providers, so we support currently 5 different hardware providers from multiple technologies. To start with, we'll look at some gate-based quantum computers. So we have IonQ, which is based on trapped ion technology, and Rigetti and OQC, Oxford Quantum Circuits from UK, which uses, they both use superconducting qubit technologies. Throughout the past year, we added a few additional ones. So this one is from Xanadu. This is a photonics-based quantum computer. So the device is called Borealis. So this is designed to support like continuous variable quantum computing. So it uses Q modes or like squeezed states of light pulses. So here, when this device was released, it uses, it's not a universal quantum computer, so you can't have, it implements a specific protocol known as Gaussian boson sampling. So, and as part of this release, they also, Xanadu released a paper showing this can achieve quantum advantage. So you can actually run yourself that particular program and explore use of GBS in bracket directly to like. And the final type of quantum computer we have added to our service so far is QERA. It's a neutral atom-based quantum computer. So this is it uses rubidium atoms, and it's for analog Hamiltonian simulation. So it's not gate-based, so you can actually simulate real physical system. It's following on from the previous talk on the quantum chemistry. Obviously, currently it supports, it has many chemistry-related simulations. There are some examples in our part. You can look at those. So those are the devices, and I just want to finish with some of the features we've added to the bracket service itself. I think there was a few mention of the hybrid jobs, like hybrid quantum and classical combination. To make this easier, we have a feature called hybrid jobs. So here, you don't need to program which part runs in your classical part or when to submit it to the quantum part. So all you do is you write your program and you can submit the whole algorithm to hybrid jobs, and the hybrid jobs feature manages running of these programs in the classical part and submitting it to the QPUs, getting the results back, doing the recalibration, and then submitting again. So it takes care of doing that hard work of doing the classical part and the quantum part, and you also get to see the live insights of how your algorithm is doing, and then you can stop, restart, or whatever you want. So you have control rather than letting it run for hours and hours. And as part of the hybrid job, you also have, we also support like high performance embedded circuit simulators. So these are again available as part of in the same application code within the containers. So there is a particular simulator from Xanadu called Lightning Qubit and Lightning GPU, which you can use GPUs for simulators as well. And some of our instances have NVIDIA Q Quantum SDK. So using that, you can run state-of-the-art simulators on the GPUs for even better performance. And recently we announced Amazon Bracket Pulse. So this is a feature which allows you to go beyond gate-based, and you can actually run your applications using pulses. So these are analog instructions that control the state of the qubits of a QPU. So this is currently supported in Rigetti's latest Aspen M2 device and also in Oxford Quantum's LUMI device. Last week, we announced, I'm going to quickly finish. This is the last slide, the algorithm library. So with the list of algorithms here, and maybe I'll finish off with how you can get started. So irrespective of whether you're enterprise, research institute, small and medium business, it's very easy to get started. You can sign up in our console. And if you want to open an account without credit card, reach out to Reza. She's on the call here as well, and we can help you with that. And we also have cloud credit for research. So if you're running a research, if you are to run proof of concept, and we can provide funding for those as well. Again, Reza is the contact for that. With that, I finish. Thank you.
Thank you.
Thank you.
Thank you, Jack. And thank you for the kind invitation to join the Amazon network. Surely interesting for many. So it would be so. Do you have any questions, by the way, to?
Jax,
No. Okay, thank you, Jax. Anyway, so now we have Himadri Majumdar from VTT, the Finnish Technology Center, and Himadri is also engaged networker in Quanti Karelia network. So thank you, Himadri, and you have also promised to talk about what we have been talking about here today. So welcome, Himadri.
Thank you very much, Christina. It's a pleasure to be here. I hope you all hear me.
Yes, we hear.
Excellent.
I
Great.
that you don't get any distraction here now, but you can start.
No problem. First of all, let me apologize for not being there in person. This would have been a fantastic event to be attending in person. Unfortunately, something came up and kept me in the capital region, so sorry about that. I hope you have all enjoyed and you are still enjoying the event. I'm going to talk about. I was supposed to summarize the whole discussions that you had in the event today. Unfortunately, I was not able to attend all the speakers, but I would try to give you a summary from a Finnish perspective, let's say. So things that has been happening over the last couple of years and within the Quanti Karelia project as well, and how we have collaborated nationally to position ourselves in Finland. So I will give you a quick overview of that. And please excuse me if I might be repeating some of the messages that you heard already during the day, because sometimes it's similar things, but it's good to repeat in a way. And in that respect, what I'm going to talk about is the importance of the ecosystem. I'm sure this came up quite a lot in your discussions. And also about the importance of the value chain, how to keep the balance of the value chain of quantum computing, because in Finland, we are very strong on the hardware. We are one of the best in the world in hardware and enabling technologies on quantum computing. But we have to still catch up in terms of, let's say, algorithms and quantum software in that respect. And these are things that we need to be aware of and try to engage a bit more in the community. And then quantum computing being one aspect of quantum technology, we also have quantum communications and quantum sensing and devices. In sensing and devices, we are also good, but we are also catching up on the quantum communication side. So how to make sure that the community is fully engaged and we have the ecosystem which is fully, let's say, active in terms of building this structure. We have in Finland set up an ecosystem called Institute Q, and I'm going to very briefly tell you about the structure and how we plan to operate. So let me share my screen with you. And please give me a quick shout out as soon as you see my screen. I hope it's visible.
Yes.
Good.
That's perfect.
Very good. Excellent. So as you can see with logo and things, we started this Finnish quantum ecosystem in 2021, a year and a half ago. And the goal of this was to have a virtual institute, which we use as an ecosystem, which brings together all the players, all stakeholders in Finland together within this structure. And the mission and the vision was very clear that we cannot be operating in an isolated structure where we focus on either the research or the education or the business, but we focus on all these aspects. And this is exactly what we have put forward from the very beginning, that we work on creating the next generation of workforce through education and training, and also retraining existing experts, for example, in AI, who might be valuable for the quantum algorithm community. And then also keep up the excellent research that we have been doing in Finland, and have the latest and best infrastructures as well. You probably have heard in the news that very recently we combined the Finnish quantum computer Helmi with the Finnish supercomputer LUMI. And this is one of the first in the world to come up with such an infrastructure. And these are the things that we should do more. We should keep up and stay ahead of the game, so to speak. And then innovation and business are things that are obvious, because that is how we create impact in society from the sort of both commercial and societal perspectives. And these are the things that we have to keep engaged. So all these things have to come together in this ecosystem. That was the expectation from the very beginning. And to start with, we at VTT worked together with Aalto University and University of Helsinki to build this structure, or build this structure from ground up. But as you can see in the bottom, there are a lot more stakeholders who are coming in. And this is a constant process where we keep on building the strengths and keep on engaging the community in more and more in this respect. And from a structure perspective, it probably is obvious that we have three structures within the Institute Q. We have the education and training structure, which is called EduQ. And there we try to create national doctoral programs, national master programs, even industrial programs where industry is collaborating with educational institutions to create new programs that is necessary for the future, and so on. So those are the things that we will go on. Even within the education structure, we have educational programs for the companies, so that those who have not been into quantum can learn how quantum is going to impact their business in future. And then research and infrastructure I mentioned already, but there a lot more also goes on in terms of training of future generation of researchers who will potentially create new business or join companies that will start their quantum activities. So I even heard, or I read that there have been now discussions in the community overall that many of the big businesses will soon start having people who are focused on quantum, and even have chief quantum officer or something in similar positions in their organization. So quantum is getting very serious in that respect. And for that, we need to create new researchers and educate them and train them from the research perspective. And then finally, innovation and business is something that we have to do to create the impact. So we have to engage the business, both creating new business and helping the existing businesses to adapt quantum technologies and quantum computing, and so on. So all these things have to work together, and this is a community exercise which creates a strength for us and make us competitive globally as well. Very briefly, Business Q. I mentioned the membership of Institute Q is constantly growing, but in Business Q we took a bit different approach, where we wanted to have quicker participation and quicker engagement so that we can propagate the message that quantum is important and it needs to be engaged. So we started the Business Q operations at the same time as Institute Q. And so far we have been able to engage quite many industrial players that you can see here, some obvious names, but some even end users like OPA is there. We have Elo, the pension company, also involved. It's only yesterday, I still didn't put the logo here. It's only yesterday we had Elisa joining this Business Q community. So we are trying to engage not just enabling technologies and solution providers, both hardware and software, but also the end users. They have to be engaged in this community as well. And that's what we are trying to do. And if I try to sort of wrap up and give you an overview how this the whole wheel works. So here you can see from the left that we have core values of education and research that we strengthen, that we had for quite some time, but we keep on strengthening with getting funding from various sources, including Academia of Finland, Business Finland, European Union, and so on. And we keep on building the core national infrastructures for that, both hardware and software. And then on the business Q side, what we are trying to do is take an approach of creating innovation and impact. So we take routes specifically perhaps related to quantum computation, quantum communication, quantum devices and sensors, and post-quantum cryptography as well, and try to incubate new businesses out of that. And not just create new jobs and new technologies for Finland that goes to the world as exports, but also strengthening the existing businesses in Finland. And there we have very strong support from Business Finland, even private investors investing in more and more in startups, and also strategic national projects like KUTI and MATQ, which enables companies to do R&D that creates their next generation of products and services. So this is what I would say is what our ambition is and what we want to do. And obviously, from Business Q perspective, we want to see Finland quantum ready and quantum safe by the end of this decade. That would be a challenge, and that would be something that we want to go for. And finally, we want to add all this up and position ourselves as a global leader in quantum technologies. It's a high ambition, but I think we have all the components in place to make it possible. And we should be aiming high with that. And I would especially like to mention and thank Olli and others in the Quanti Karelia project, which has helped us a lot to propagate this message, to help build the community, to bring people together, even from parts which were not traditionally quantum, but keep them engaged and have them create interest in the quantum technology sector. So thank you very much for that. And I hope we find a way to continue this project in one form or another in future. With that, I would like to come to an end of my presentation. Thank you for your attention. All right.
Yes.
Okay.
Sorry, it was my fault.
So thank you, Himadri. You promised to give a wrap up of our presentations today. So could you say a few words?
As I mentioned in the beginning, I haven't been able to join all the presentations, unfortunately. But what I can say is the whatever has been discussed, the importance of ecosystems comes up very often. And we have individual companies, we have individual success stories, but it's always the combined effort of an ecosystem that makes a initiative successful. And quantum computing being not so obvious, it's important to come together and work together to build it up. I mean, it's a learning process, which, for example, how it has worked with AI community. So we need to learn how they have come together and work together, and also do the same thing with quantum as well. So that would be my strong wish from this community.
And that was a great comment and addition to your excellent speech, Himadri, and thank you so much for joining us and being a part of this network also. And yeah, I wish you a happy Christmas, maybe.
Same to you all there. Thank you very much.
Our presenters who are here, Mikael, Mikko, Tuomo, is Tuomo here still? I don't know. Ah, there you are. So Tuomo, Mikko, Mikael, please join us here for a while. We need chairs. Please grab a chair with you. So this is kind of a self-service panel.
Petri would appreciate that.
So we are going to have just a short panel here to answer some questions. And if you have questions, please comment on in Teams, the comment chat box. So yes, gentlemen, thank you for joining us here. So you will let us know if there are some questions. But just to start, I would like to ask you all, what's next in quantum computing? And Mikko, you can start.
What's the next big
What's
thing?
yes,
let's say?
yes.
Because we are every day we're doing very good progress. The field of superconducting quantum computers especially is developing extremely rapidly. If you have a good idea today, in 2 years somebody else will have the idea, because there's so many smart people working on this. And after this Google quantum supremacy work, that was already, in October 2019, when the quantum computer was shown to calculate its native problem faster than any supercomputer on the planet. Right after that, I said, okay, that's great, but how can we prove it? Could we have like a provable quantum supremacy where we could check later on with a classical computer that actually the quantum computer did calculate it right? And that was not the case in Google's work, not the case in later work by the Chinese groups. So I think that would be the next big thing in the field, to have provable quantum supremacy. It could be quantum advantage, like useful quantum advantage at the same time. I'm not sure. That's a big question, but at least provable quantum supremacy, I think that would be, or checkable quantum supremacy, I would say, that would be a very big milestone towards commercial quantum advantage.
Wow, that sounds fascinating. This fascinating situation that we are kind of waiting for something new. Tuomo, what about you?
Well, since I will probably remain kind of an outsider, certainly to as far as real quantum computing is considered, both Mikael and Mikko are involved in that. I will not make any forecasts to that, but I realize, and actually quoting Sabine Ostenberger now, I remember that physics needs this kind of flagships, this kind of a banner under which it should unite itself, and also raise once again this sort of overall excitement about what will come next. And I think quantum computing basically is the flagship right now. We will not be building any bigger particle accelerators in the near future. Rather, we try to build better quantum computers. And that money probably is better spent that way. So I see this already, for example, witnessed by Morten's description. This is one of the central themes, that we get like a new community of thinking, which also will spawn some new ideas. And on my personal interest in this, and maybe on that side, I think that it's also the algorithmic side. Now that both of you have said that quantum is different, and I agree with that. Exactly how? So now that what actually separates quantum computing from an logical, formally logical point of view from a Turing computer? And that issue will probably spawn a lot of research and also new quantum algorithms. So that's the direction I'll be looking at that from my point.
Yes, so I think Tuomo's comment on this, that it's an exciting field, and compared to particle accelerators, I think that quantum computing really is a highly interesting topic also from a public point of view. So you really see it in media more and more already, and I think in general quantum computing can help make science more exciting for the public. And I think this is, for near-term impact, I think this is already happening, and I think that this is before we get the quantum advantage that Mikko mentioned. So before we are there, already this showing that technology and science can be really cool, and getting out the quantum weirdness to a much larger audience than before. I think that's really exciting, and in that way it is comparable, if not even exceeding, the Large Hadron Collider, for example, that I think everyone here in this audience has heard about, but it would be interesting to actually have some sort of a poll of the average person on the street that have they heard about quantum computing or the Large Hadron Collider. And I think that presently, at least, quantum computing has been so much in the media that I think it gives hope that humanity, when humans and engineers and physicists and all of us, not all of us, but those that do this, can manipulate quantum states in such an intricate way. So I think it's a very positive message for humanity that even if it's not, you cannot do anything faster with quantum computers, but just the fact that you can do something with them is already so exciting that I think it also increases the hope in the general population that science can be a solution to all sorts of problems, not only computing problems, but it really shows how far we have descended from the time when we can climb down from the tree.
Yeah. So I visited London, I think a month ago or something, and I went to this museum, science museum, and I realized that just 90 years ago, how did we solve differential equations? Do you know? What was the best way to solve differential equations 90 years ago?
I guess a book.
No. Well, one of those, but I know because it's said in our theory. We are solving the differential equation of getting a projectile there by purely mechanical means.
Exactly.
Mechanical, optical, arrows, prisms.
It's a mechanical machine.
Right.
That it was used to solve differential equations. So you were rotating some wheels, and that would integrate you inside the differential equation. So in 90 years, we have gone from mechanical computers to quantum computers.
Yes.
I think that's amazing speed that we have developed these machines. If you look what's going to happen in the next 90 years,
Right.
who knows?
But that brings me to a very exciting philosophical problem. How is it possible that electrons or entangled qubits inside some microscopic device can actually reproduce the atmosphere of the Earth in such a way that when you, after a week, go and take a satellite image of the clouds, you could have equally well produced the same picture from those little minuscule electronic atoms. How is it possible that such a correspondence exists? And you pointed to the other side of that same equation, the fact that actually mathematics can be computed with steering wheels and so on. It solves differential equations. So there must be some kind of very mysterious relationship between reality and then our theoretical means of presenting it. And this is also why quantum computing provides. I think one of the points that came up in several presentations, maybe from you both as well, that we, and Antti in particular, we have to stop trusting computer simulations as exact truth because we now know they are imbued with this uncertainty.
Yes. Hey, we have still Morten there. Morten, how do you think? What is the next big thing in quantum computing from your perspective and Danish perspective? Are you with us? Morten, are you? Maybe he's not there. What about Jats? Are you online? They are online, but maybe not listening so much. Okay.
Can you hear me now?
Yeah, I know. Okay. Hi.
All right, cool. Yes. Well, what we are trying to look for in particular, as I mentioned in my talk, is the sort of the life science applications and trying to open them up for. And then I was very inspired by the talk that we we saw today, for instance, from the drug development perspective by Antti Poso, and these are exactly the same things. Just a minute.
Problem.
I had another call open. Sorry about that. Yes, we are trying to develop these life science applications. I hope you can hear me now. Yeah. And these things are very complicated, as I mentioned in my presentation. So these are not some things that are coming up in the next 5 to 10 years. So we are trying to figure out what are the sort of near-term applications that we can develop. And I agree with some of the things that have been said today, that quantum machine learning seems like a low-hanging fruit, because some of these algorithms can give very immediate impact once we start working on them. And it's, the challenge I see there is that the people that work in this machine learning community, they are already they already have very powerful supercomputers, very big data. They have lots of data, they have lots of things to solve. So it's a little bit difficult to engage with them, in my opinion, and say, look, do you want to engage in quantum? Because what they do now already works quite well for them. So there's a challenge there, in my opinion, to get them on board. But they would be the most interesting cases to investigate at the moment, because some of the things that you want to do with a fault-tolerant quantum computer are so complex that it's much beyond what we can do today, and then what current hardware technologies are ready for.
Thank you so much. I have one question also about what should the governments in different levels, national levels, maybe municipalities, but also EU level, what should they be doing? What should they do to enhance and make this development more effective and then also socially just? Tuomo, do you have some ideas about this? Shortly, please.
Social justice is hard. I'm afraid this sort of technology is going to remain elitistic for quite some time to come. So I don't have any short answers to that, I'm afraid.
Okay.
Otherwise, I think the model, the Danish model, we suddenly realize, there's a branch of Danish government, as you described it yourself, Martin, in a way that has also all the freedom that a private enterprise, like your foundation, has. That's a very interesting combination, and probably could work well in science. I was actually listening to you. I realized, Niels, the reason why Denmark, in my opinion, is so good in quantum physics lies with Niels Bohr and maybe even his brother Harald Bohr. And they also were actually, as far as I remember, rather wealthy people. Niels was married to a princess or something, and so the community he created in the Copenhagen School of Quantum Physics is famous also for that. So maybe you, Martin, are now continuing that same tradition. Provide ample funding, and eventually something very beautiful will come out of it. How democratic it will be.
Well, Danish is a democracy, so we can trust, or what more, we can trust that it will be also democratic. But let's hear about Mikael, please.
Yeah, sure. Tuomo said funding, and that's important, I think. But I think at least as important is just a dedication and a commitment to develop quantum technologies, and then especially also from an education point of view. So I think Mikael knows very well that it's rather difficult to find good people to work here. But I think everyone also needs to find a balance that because it is a risky business. So the role of the government here would be to to somehow find a balance in the educational programs of what are we educating. So it should be broad enough to be useful also in the unlikely event that after 10 years quantum computing fails. Then we cannot have as was mentioned here in the quantum Karelia, we cannot not have 17,000 quantum computing experts that know nothing else. So I think finding this balance between educating people that have the knowledge of being useful in the quantum technology field, but also broadly elsewhere is important. And I think also this shift from being just a physics-based education system to really include much more broadly quantum expertise from other fields is necessary. And then if it needs to be a complete education program, I don't know, but I think a bit like I'm old enough to have actually been on some of the first just user computer courses in primary school, and I learned how to actually type, and then we had desktop that one was supposed to use a keyboard and get correct sentences out. And that seems, of course, trivial now, but it's still only 30 years ago. And I think that this sort of a quantum awareness needs to be put into students' heads at an early stage. If primary school is the right one, I don't know that. I think there's much better experts in answering at what level it should be done, because, of course, one also needs to remember that quantum technology is a very complex field. So we cannot expect that everyone even can be an expert here. But I think the quantum awareness and curiosity should be somehow awakened at a rather early stage, because that then helps people choose their own careers and just know that something like this exists when people, especially in high school, are already starting to think, so what will I do when I'm big? And starting to choose already when they choose, if they go to Lukio, is that high school now in English, or somewhere else, then one already needs to start making these decisions of what do I want to become when I'm big. And I think then the knowledge of the option of that you can become someone who knows quantum computers should be put out there at an earlier stage.
Thank you. Okay, so I have promised to use this if we don't stop in time. So I give the last words to Professor Möttönen here, and be short.
Right, thanks. Yeah, I kind of agree with Mikael that the governments, they should now invest into quantum computing, quantum technology. There's a lot of risks in the companies, not only in our company, but in other companies as well. And part of that risk in this early technology should be carried by the governments, just to lower the risk of the private investors. And not only in equity investments, but also there should be this kind of SpaceX sort of model where the governments buy quantum computers from private companies. And this is, of course, happening already in Europe, on the EU level, in national levels. That should be continued. We want to build the quantum computers for customers, and that's the most efficient way of making them useful and working. About education, I think there is a big problem here, because the companies in Finland, we are hiring now more quantum engineers than we take into the university at the moment. And those people who get into the university, today, it will take them quite a number of years, at least 5 years. That's a minimum to be a quantum engineer. So imagine where we would be in 5 years, and we should now kind of respond to that demand, at least. So, and I kind of disagree with Mikael about the point quantum computing failing. I don't think that it can fail. It can take a bit longer. That's of course, it's about the time scale. I don't think that it's about a failure or not. So that's true. And also, when we educate these quantum engineers, they are useful also for other fields. I mean, I know that there's like 5 at least more than 5 job descriptions, and all of those skills can be used in other industries as well. So I think if we start educating them now, it's not going to be wasted talent.
I fully agree, and I just want to jump in before Christina hits me in the head with the hammer.
It's coming.
Yes, that I also don't think that quantum computing will fail. I think that's just the worst case scenario, and one also needs to take that into account. I don't think it will realize itself. I also believe that quantum computing in some form will be very useful.
Okay, I thank you, panel. Please, we are going to have the closing words with Jarmo and Olli, and you can also present the comments that have.
Yes, Jarmo,
Yes.
you could say the comments were there.
Yes,
Please join us here. And,
there is a one comment and one question here in Teams chat.
Okay.
Himadri comments that quantum needs PPP for some more years to come. Governments have to work together with private investors to make sure both academic and applied balance is maintained. And SAM Joensuu asked a question, maybe you can find the quantum connection to this. What do you think about the metaversum now and near future?
okay, I think you can answer that question when you come here and present your closing words. Thank you. But thank you for the time.
I think that we will have very quick closing words, and these are just come on. As a Quantum Karelia project, we are now come to the end where this project that started about 2 years ago is about to end. Of course, we still have some runway to go there. I mean, about 4 months, we have extra time to complete our reports, and they will be sent to you, as well as also the materials now. This has been recorded, it will be sent to you also, so you can study. Of course, we try to make some editing, isn't so? At least some, because it seems that there are too many times started the introduction and we didn't have the sound, so we can edit it to a nicer form. But I have to thank you all. Thank our presenters today. Isn't it so? The marvelous happening, marvelous venue in general, and we are very humble about this, that you came here and you saw it important enough to come and present your ideas with us here in this. It's very important to us. We humbly thank you for this honor that we have had working with you, and also how nicely you have taken us with you in the same society of you could say that family of Quantum. I mean, we feel that we are now members. We're qualified members. And what would you think if you would say also something like, what will be the next step as an expert of ICT area, and you'll be now getting all this information? What is your kind of like final remark?
Very easy question for the close.
Yeah.
I think you said enough, but I also like to thank all the partners and who have participated in this project. What will be the next thing? I don't know, but let's find out.
Yes, but
the next project.
Yes, exactly. I was trying to kind of fish out that you would have said that. We are actually in the brink of planning a new project, and it will be first kind of intermediate project here, but then we are trying to compose a larger project, and we will invite all of you who are interested to do counterparty projects, and we think that we will make a huge project. And I think that the Himadri's comments in the end, kind of like also inspired us to kind of like, it gives us a great inspiration also to continue this work, because I think that also Mikael said that it's a larger issue than just experts, and Mikael has always said that also, that you have to have all these people, different kind of people, different kind of expert, different kind of topics, and different kind of we would say that disciplines in that sense work together. And I think Morten's message was pretty much the same, and they have already made some actions towards that. And I think that we should a little bit follow the good steps and, you know, try to do same kind of actions as I think Tuomo pointed out, that it's something that's very important. But
maybe in the next project there will be also some kind of more pragmatic work.
Yes.
In practice,
Yes.
there are services, hardware, software, tools
Yes.
available. A lot of things have been developed hugely during these 2 years, so maybe we can make a little bit more hands-on also. Of
Yes.
course, develop this networking thing, sharing information of the bleeding edge state-of-art
yes,
technologies, but find some places where to utilize this
exactly. And
software and all the other tools.
yes.
From quantum computing.
But I think we are almost in the brink of the end of the time. So yes. Yeah, and let's go further before she comes and hammers. Yeah, okay, I'm the one to get the hammer. Okay, anyway, I had those reserved for the evening coffee, those chocolates there. But as you noticed, I hope I didn't disturb you when I was ripping all the papers off there. But please help yourselves when you go out of this room and take something as a treat from us, you know, make it leaves a sweet taste in your mouth. As the last thing that you can remember of this project. And so I think that this is about it. And this is not the end. I think this is just a small pause, I would say. Okay, thank you.
One thing to Christina,
Yes.
because it came from during the break from Mikael. We can literally say quantum computing is really cool. 10 millikelvin, right? So
Yes.
you need to promote it. Okay.
Thank you. And now, if you want, you know, you can also take. Here are the hands out that you could have taken also. You know. So, but you can take them as a keepsake, and you know, kind of like you can read about these presenters of today also. From these.
And applause to Olli and Jarmo.